Hello, everyone. Today, we are very excited to present our paper on computing complex temporal joint queries efficiently. This is the outline of our presentation today. Let me start with the problem definition of temporal multiple joints. Temporal data analysis is an essential feature of modern database system, as most of the practical data are temporal in nature. Consider a toy database storing the collaboration network among authors. For example, the interval from 2011 to 2015 on BC indicates that B and C collaborated over this 5-year time period. A temporal joint can find a chain of 4 authors collected by 3 pairwise collaborations simultaneously at some time point. For example, ABCD. In contrast, a non-temporal joint would find AEBD because even though each of the 3 collaborations exist at some time point, they never took place simultaneously. One may further consider finding durable collaborations, which has persisted in the database for a sufficiently long time. For example, this figure counts the number of such patterns in the entire DBLP collaboration graph at different durability threshold levels. Now, let me give a formal definition of temporal multiple joints. A natural joint, which is also called a non-temporal joint, is defined on a universe of attributes, and M relations is defined on a subset of attributes. Each relation consists of a set of tuples and data records. So a tuple defined over the universe is a non-temporal joint result if its projection onto each relation is a valid tuple. A temporal database further associates each tuple with the valid lifespan as an interval. The temporal joint results are defined on top of non-temporal joint results such that the valid intervals of participating tuples should have non-empty intersections. Our solution to the multiple temporal joint queries can be extended to other temporal predicts. Due to the time limit, I won't go to the details, but you can find many interesting transformations in our full paper. Next, I will give an overview on our theoretical results. We know that a non-temporal joint can be computed in linear time if and only if the joint is acyclic. For general joints, there is a line of algorithm using tree decomposition strategies, whose cost is measured by the notion of width, such as fractional habitual width. Our first result shows that a temporal joint can be computed in linear time if and only if it is hierarchical, which is a strictly subclass of acyclic joints. The lower bound is achieved by reducing the triangle listing problem to any non-hierarchical temporal joint evaluation problem. Furthermore, we show an efficient algorithm for non-hierarchical temporal joints based on 2 query-dependent quantities, the fractional habitual width and hierarchical habitual width, measuring how far the joint query is away from being hierarchical, which is a new notion of width defined in our paper. Next, I will go over 3 approaches for achieving those theoretical results. The joint first approach, namely first computes the non-temporal joint results, and then filters each result using a temporal condition. This approach has the same complexity as evaluating a non-temporal joint, but this is not output sensitive anymore, as the non-temporal joint size could be much larger than the temporal joint size. Corresponding to the joint first approach, we present a time first approach, also known as a sweep plane-based algorithm in the literature. Intuitively, it sorts the endpoints of valid intervals first, virtually sweeps a time axis, and maintains the set of active tuples whose valid interval is intersected by the axis. More specifically, for each endpoint encountered, we distinguish 2 cases. If it is an insertion of tuple T, we just add T to D. Otherwise, we enumerate all the joint results participated by T if there exist any, and remove T from D. The correctness behind this algorithm is that each temporal joint result must be the non-temporal joint result of D at some time point. Then our next question is how to organize active tuples in D for supporting insertion, deletion, detection, and enumeration efficiently. We maintain a special tree index for hierarchical joints, where each leaf node stores 1 relation, and each internal node stores the intersection of projection of the children nodes onto their common attributes. In this example, we have 5 relations corresponding to the leaf nodes. For node AB, We first compute the projection of relations R1, R2, R3 onto AB separately, and then compute their intersection. The relation for node AC and A are defined similarly. Then how to use this data structure to support the different operations? Let me use this example to illustrate the high-level idea. When A2C1F1 is inserted, we first insert into the leaf node. As A2C1 does not exist in R4, but exists in R5 before this insertion, it will be propagated to node AC, and A2 will be propagated to the root following the same rule. Symmetrically, when a tuple is deleted, say A1C1F1 from R4, we first delete from the leaf node. As there exists another tuple with value A1C1 in R4, this deletion will not be propagated to the parent. If we further remove A1C1F2 from R4, this deletion will be propagated to the parent, but not to the root. Next, to check whether an input tuple participates in any join result, it's easy to check from the leaf node to the root whether its projection exists in the corresponding node as a valid tuple. For example, A2B2 will participate in some join result, but A2B3D3 does not. Finally, when an emerging join result participated by some tuple, say A2C1F1, we recursively invoke this procedure on the left and the right subtree separately, and then combine their result as a Cartesian product. Now we come to the complexity of this algorithm. The initial sorting takes n log n time, and each single operator takes log n time if indexes are prebuilt. And the enumeration takes kt time, where kt is the number of join results participated by t with the active tuples defined by its right endpoint. Over all iterations, the total complexity is n log n plus k. We can also apply this approach to arbitrary acyclic joins, but here we don't enjoy such a nice data structure. Instead, we can invoke the non-temporal join algorithm on the active tuples from scratch when enumeration is required. But this step will incur a cost of n plus kt. Over all iterations, the total complexity would be n squared plus k. Next, we turn to general joins by borrowing the powerful tool of generalized hypertree decomposition. Intuitively, a GHD of a join query is a tree whose nodes are a subset of attributes, satisfying the attribute connectivity and the relation coverage properties. Our hybrid approach based on GHD works as follows. We first compute the temporal join results for each node using the join first approach and materialize the join result as an input relation. Then we are left with an acyclic temporal join and invoke time first approach. We next come to the complexity of this hybrid approach. Each node in the GHD can be computed in time of the AGN bound, as well as the size of the join result materialized for this node. And in the last step, if the GHD is hierarchical, we can achieve a linear formula in this form. Otherwise, we get an extra factor of n in the complexity. Based on these two observations, we introduce two notions of width for a join query. The fractional hypertree width measures how far a join query is away from being acyclic, which is defined as the smallest width over all GHDs. The hierarchical hypertree width measures how far a join query is away from being hierarchical, which is defined as the smallest width over all hierarchical GHDs. Then our hybrid approach has the time complexity related to the minimum between hierarchical hypertree width and 1 plus fractional hypertree width. But the relative ordering between these two quantities is unclear for general joins. As a brief summary, we provide a guideline of choosing the best evaluation strategy for temporal joins. This guideline is built on the worst-case analysis, so multiple best candidate algorithm could exist for some queries. We don't distinguish those theoretically equivalent methods, but we can see their difference in the experiments.
Finally, we saw some experimental results. We implement all algorithms in C++ and we run all our experiments in a Linux machine with 256 gigabytes memory. We compare all different variations of our algorithms with a baseline algorithm that is currently the state of the art to handle temporal join queries. In particular, we implement our time-first hybrid and hybrid interval, which is an optimized version of the hybrid algorithm. We compare this algorithm with a baseline approach where sequentially picks a pair of relations to join and materializes their join results as a new relation to be further joined. Two relations are joined using the well-known forward scan-based algorithm, which has been experimentally verified as the most efficient temporal join algorithm. We also implement another baseline join first, which computes all subgraphs, matching the Curie pattern using known subgraph matching techniques, and in the end, it checks the validity interval for each subgraph. The main goal of our experiments is to show what is the running time and the memory usage of our algorithm and the baseline algorithms under various Curies and under various synthetic and real datasets. The types of Curies we tested in our experiments are simple practical Curies, such as line, star, cycle, and bow tie joins with different lengths. First, we saw the results on synthetic datasets. Notice that one drawback of the baseline algorithm is that it computes the overall temporal join result by solving pairwise temporal join Curies. Hence, the efficiency of the baseline depends on the size of the intermediate results by the pairwise temporal join Curies. For each different type of Curie, we create a synthetic dataset in such a way so that the number of the intermediate results between any pairwise temporal join is large, while the number of final results is small. In our paper, we describe exactly how we can design such a synthetic dataset. In this figure, we show the running time and the peak memory usage of all the algorithms we study as a function of the durability threshold. As we can see in the figure, for any type of Curie, our best algorithm runs extremely faster and uses extremely less memory than the baseline. For example, our algorithms for line join Curies run 70 times faster and use 1,000 times less memory than the baseline. Next, we compare the running time of our algorithms with the running time of the baseline on real datasets. First, we use the TPC-BIH dataset, which is the bitemporal version of the well-known TPC-H benchmark dataset, extended with different types of history classes. QTPC Curies are performed in these datasets, which are simple line joins, such as customer is joined with order and order is joined with line item. Furthermore, we use a small dataset called fly dataset, storing flight information. By conducting self-join operations on its edge table, we can test line, star, and cycle join Curies. Finally, we use DBLP, which is a large common ego network for DBLP. Again, by conducting the self-join operation in the graph, we perform line and star temporal join Curies. Now let's see the actual results. On the y-axis, we show the running time as the ratio to the baseline algorithm. On the x-axis, we show different types of Curies on different datasets. In TPC-BIH datasets for the QTPC3 Curie, only hybrid interval can slightly outperform the baseline. The main reason is that the relations involved in these Curies generally have low multiplicity between join keys, so the number of intermediate results is small. However, when it comes to QTPC9 having more intermediate results, we see that our proposed algorithms run much faster, even 10 times faster than the baseline. For line and star Curies in the DBLP dataset in the right side of this figure, we observe that join first performs the worst. In contrast, at least one of our approaches offers up to 2 times speed up over baseline. Finally, on fly dataset, which is a small graph with 650 vertices and 1700 edges, join first wins on simpler Curies such as line 3 and star 3, but can be more than 10 times slower on more complex Curies such as line 5 and star 5. Similarly, in this figure, we show the peak memory usage of all algorithms as a ratio to the baseline. The results are similar to what we saw in the running time. Overall, our algorithms use much less memory compared to the baseline and join first algorithms. In summary, baseline and join first run efficiently in some special cases, such as small number of intermediate results or small datasets with a small number of non-temporal join results. However, in almost all cases, our new proposed algorithms run much faster and use less memory than the baseline and join first algorithms. Overall, our temporal toolkit is more robust and scalable to Curie types and input size. In addition, we find that the performance of our proposed algorithms, time first, hybrid, and hybrid interval, varies depending on the Curie structures, which verifies our theoretical findings. With that, we conclude our talk. Thank you.